Hello. Hello. The next experiment is E9, Le Chatelier's principle. Before we go into Le Chatelier's principle, a quick brief introduction to equilibrium constant and what it means and how it is determined in a very brief session. So, equilibrium constants are calculated or derived for expressions in which the reactions do not go to completion. Therefore, after a certain period of time, what happens is the reactants undergo product formation, and after some time, the products start decomposing back to the reactants, and hence thereby never going to a completion. So if such a reaction has to go to completion, then we will have to use some other technique to remove one of the products that is there, in which case the reactant will go to completion. Now, the equilibrium constant, because it is at equilibrium, we have the rate of the forward reaction is given by the concentration of the reactants, and the rate of the reverse reaction is given by the concentration of the products. The concentration of the products and reactants are always expressed in moles per liter or in terms of atmospheres, so that we can find out which expression to be used. When the equilibrium constant is expressed in terms of concentration, then we can write the terms that do not have the concentration terms on one side of the equation, and the other side you will have the terms containing the concentration terms, so that in R, the rate of the forward reaction is equal to the rate of the reverse reaction. Therefore, the rate of the forward reaction is Kf for the reacting concentration, which is equal to Kar, the concentration for the products. The exponents for the reactants and products are always derived from the balanced equation that you have to write. And so now the term letter K, which is the specific rate of the reaction, has no units in terms of concentration. So we can write the ratio of Kc over Kr is equal to the concentration of the products divided by the concentration of the reactions. And this is equal to the capital letter K, stated or called as the equilibrium constant, written as Kc because we are talking about the reactants and products in terms of concentration. However, if you do the reaction in terms of gases, then you will write the reaction in terms of Kp, and over there, each concentration of the gas or the reactant or product is expressed by using the ideal gas equation, which states that Pv is equal to nRT. The term concentration then becomes equal to RT over P. Or we can write it as N over V is equal to M is equal to P over RT. And once we write that, then we can solve the equation and change everything else. Now, whenever a reaction takes place, and if you have to make it to go to completion, as stated earlier, you have to remove one of the reactions. As soon as you remove a reaction, then you are going to put a stress on the system. And so the next and actual topic for this particular experiment is the Le Chatelier's principle. What does the Le Chatelier's principle say? The Le Chatelier's principle states very simply that the reaction proceeds in a direction opposite to the direction in which the stress was applied to that particular reaction. Now, the only way the equilibrium constant K can change is it changes with temperature. Otherwise, whatever calculations you do, you will have to get the equilibrium constant for each of the reactants and products at any given time. Now, when you apply a stress, the question comes, what are the stress that can be applied to a reaction? And the answer to that is you can apply stress in terms of by adding excess of reactants, excess of products. Then you can change the pressure, change the volume, include like non-reactive substances to the reaction, and of course change the temperature and see what happens. But everything, the direction of the reaction will be always such that the equilibrium, the system comes to equilibrium as fast as possible. So in this case, there are three states that will be there. One, when the system is in equilibrium, you get your K. When the system is not in equilibrium, then this expression is called as the reaction coefficient, and it can be greater than or less than K, and this will predict in which direction the reaction goes. Once you have some idea, today I'm going to share my screen. Now I'm going to share my screen so that we can do the experiment. And again, this is a very short experiment. So go to new file. I don't want to save myself, and then go to Le Chatelier's principle. Le Chatelier's principle in cobalt complexes. And this is a really beautiful experiment because what happens is the cobalt chloride solution in water and in its actual complex formation has two different colors, and we can just determine by looking at the color which direction the reaction is going to move. So that's what they say. In this experiment, we'll examine the equilibrium between cobalt hexahydrate complex and the cobalt tetrachloride 2- complex. The following equilibrium is observed, and you can see that CO, H2O6, 2+, aqueous solution plus 4 chloride ions aqueous. On heating it gives you the COCl4, 2-. So now we have to apply heat, and on the other side you get 6. So whenever you apply heat, remember that it's an endothermic reaction because heat is absorbed by the system to undergo change. And exothermic means heat is released. This reaction is endothermic, so adding heat causes the equilibrium to shift to the right, making the solution blue. Cooling causes the equilibrium to shift to the left and making the solution pink. When HCl is added, there is more Cl, and therefore the equilibrium will shift to the right, and the solution turns blue. When silver nitrate, a neutral compound, is added, because the strength of the silver ion, or the ionic strength of the silver ion and the nitrate ion is added, the chloride is removed from the solution as AgCl, and the shifts the equation back to the left, and the solution turns pink again. And so you just have to perform these experiments following the procedure and exactly observe what happens. In order to do that, I'm just going to do the first part, and then you can continue and do the second part, the remaining 4 parts. So 1, 2, 3, 4, 5 parts are there. I'll just do 1, so you can see what is expected, and then enter it in your observation table. And just use those observations and the pictures to complete your result and discussion. So what we need is get 100 ml beaker from the equipment menu, go to beaker, get out 100 ml this beaker, go to the chemicals, add 20 ml of the cobalt complex. It says add 20 ml. So here is the dialog box, add 20 ml and say, okay. And there you can see the pink color. So now record the color. So you have to record the color. Now, after you record this color, it says obtain a pipette and add 10 mL or 2 HCl. So go to the equipment menu, look for a pipette that's 10 mLs, and then get click on the pipette to get the chemicals, and then you add hydrochloric acid, and you need 10 mLs of that, or 10 mLs, and say, okay, so now the pipette has 10 mLs. So now I'm going to adjust this, then adjust that, and 10 mLs of 2-MHCl to the pipette, start releasing from the pipette into the beaker. So you say release the liquid, and then you see the color. And that is the end of the experiment. And with that, just as before, you follow the template, complete all the reactions, write down the results, discussion, conclusion, homework, and we are done with the experiment. And so I'm going to stop the share and then finish the experiment.